record on this computer, and we're beginning. So good morning. It's Thursday, the 23rd of April. Oh my gosh. This is our second to last class. Next Tuesday will be our first to last class, and then next Thursday will be our last class. And I'm pleased to say a lot of what we've been doing for the last, several months together is culminating in what we're doing today and Tuesday at looking at linear regression. Linear regression is probably one of the most useful tools in a modeler's toolkit, in an engineer's toolkit, and just about in anybody's toolkit, because it allows you to fit simple linear models to data sets. And those that can be lines or they can be planes. We consider a plane a linear model, and the planes can be hyperdimensional. So it's very, very useful, and we'll get into that in a moment. But before we do, as always, I'd like to ask if there's any questions on the last bit of hypothesis testing we covered on Tuesday or anything else.
No questions from me.
Well, I would imagine some of you might have the question, where the hell's my homework? So let me talk to you about that for a minute. My grader and I have been having a little back and forth issues on the homework, but he got back to me at 2 this morning, the homework that was turned in on the 13th of April, and I expect the homework that was turned in on this Monday to be back tonight. And so I was thinking, instead of trying to do 17 emails times 2, is to dump them both together into one email and send them off. I did send off earlier this morning all of the graded quizzes from last week, which if you took the quiz, you should have received. I acknowledge that this is not stellar performance in terms of getting you prompt feedback. And I'm not going to make excuses about it. I'll just try to get it back to you more quickly. Any other, and notice I even recorded that for posterity. Any other questions or comments? Okay, then let's pick up and take a look at some simple linear regression stuff. And I'm hoping you can see my slides at this point.
Yep.
Okay. So let's talk just a quick review about lines and planes. So you may remember lines from middle school being of the formula y equals mx plus b, where b was an intercept and m was a slope, and m was from French from mountain. And you probably played around with lines a lot as going through. We're going to parameterize it a little bit differently. We're going to have a series of parameters for our line, and beta naught is going to be our intercept. And then depending on how many predictors we have, we'll have a slope predictor for each one of these. Beta 1, if it's a simple line. If it was a two-dimensional plane, we'd have a beta 1 and a beta 2 for the parameters, slope parameters for the plane. And I think if you had a calculus course, you may have seen normal vectors defining a plane. Does that ring any bells to anybody? I get a yes from Rocky on that. Not getting a whole lot of love talking about normal vectors. But again, there's a relationship between these slope coefficients, the partial derivatives, the normal vectors, and in your physics modeling with planes and normal vectors. You should have seen a TNB model somewhere along the line, all that good stuff. We're not going to get into the applications too much of what you do with the line or the plane when you've modeled it, but we're going to spend a couple of days now about how you determine these coefficients from data, and then how you can make statistical inference about the coefficients in particular. Okay. So here is our line plotted. And again, we've got y equals beta naught plus beta 1x. And the intercept is a distance on the y-axis from the origin where the line intercepts. And beta 1 is the slope, the traditional rise over run, and it's constant for all values of x. And that's what defines a line. Okay, so what we're going to do is we're going to talk about a regression model where we've got an underlying, where a line gives us what the mean of our random variable is, and our variance is going to be our variability is going to come from an error term that's added on to each estimate, and that error term is going to be normally distributed with mean 0 and some variance that we don't know. Okay. So what this is going to mean is that y is a random variable, and the expected value of y is going to depend on the parameters beta naught and b1 and what the particular value of x is. So in particular, we've got that the distribution of y given x is normal with mean beta naught plus beta 1x and a variance that's sigma squared and fixed for the same for all values of x. So as you go from ones to tens to hundreds to thousands on your value of x, your variability doesn't increase. It doesn't depend on x. And so what this error is the vertical variation above and below the deterministic line that gives you the conditional mean that represents your sampling variability. And again, this error is not affected by the scale of x or y. Okay, so because we've got these errors, we can have this true regression line here, and then we can have data that is scattered above and below the regression line because, for example, oops, you get a value for E4, the estimated value when x is equal to here, right around here, but you have an error term added on which makes your y bigger. Or you might have an error term subtracted. So E1 is a negative term, E2 is a positive term, and these are random differences that mean that we're not seeing the true regression line, we're seeing the regression line with noise. And the question, of course, is how do we extract the true underlying regression line with the parameters beta naught and beta 1, given that the data has noise? Okay, so run through the setup for a little bit of this. We're going to treat y as the predictor, and we're going to assume that it's known and certain. As a practical matter, there may be some small measurement error that goes along with the different values of x, but for our purposes, we're going to assume that it is known and that it is has no variability. If we say x is equal to 2, by God, it's 2, it's not 2.1. And we're going to assume that y, the response that we measured, is going to be accurately measured, and it's going to be exact as well. Okay, so we're not saying that we've got some model error plus some measurement error that tacks. We're to dump all the errors into the model error. So given this, what we don't know, since we know x and we know y, and we know a bunch of pairs of x and y, what we're trying to do is estimate the 3 model parameters, which is a slope, the intercept, and the variance of the error term. Now, because these are going to be estimated from the data, the XY pairs, and because the Y is a random variable, that means in terms that these estimates themselves will have sampling distributions and will have some associated uncertainty. And we're likely never to know their true values, but what we can do is estimate what their standard errors are. And remember, standard errors were related to the underlying variability divided by the square root of the sample size, which means as we take more data, we can get a more precise idea of what the plausible range of values would be for all three of these. Okay, so once we have this fitted model, we can use that for trying to decide what the mean value of y is given x, which is again is going to be a function of x, and also to use that to make predictions about future values of x, either interpolation in the data set or extrapolation where the values of x are outside the measured range of the data we had. And I just want to say that I spent an entire year in graduate school studying regression from Sandy Weisberg and Dennis Cook at the University of Minnesota. And it was my favorite subject. It is so cool. It is so rich. There's so many relationships between linear algebra and real analysis and optimization. Just so many things come together in this subject, and it's such an immensely useful subject. A lot of what I've done professionally in my academic life has been based on modeling, and underlying all those models is usually an attempt to linearize the data and fit a linear model to it, and then go back to the original scale. So in our 2 days, we are only going to scratch the surface. But I just want you to recognize I'm handing you a very sharp knife, okay? And I'm teaching you basically how to sharpen a pencil, but there's lots of other things you can do with that sharp knife, including hurt yourself, so be careful. Okay, so what we're gonna call our fitted model is this y hat here. So I've got a y hat, estimated value of y, where I've got b naught and b1. And b naught and b1, I'm using Roman letters. Those are going to be estimates for my slope and my intercept parameters. And so for the line I estimate, there's going to be a vertical difference between the fitted value of y hat, which is the fitted value of y, and the observed value of y, and that's going to be a deviation. Okay, so if I have my fitted line exactly right, then the E sub I, which is this residual, how much difference between y and the fitted value, is going to be an estimate. It's going to be an estimate for the unknown error, epsilon. Okay, and if the fitted lines are exactly the same, then that epsilon is going to be the same as the E, and the residuals are going to exactly match. But if the fitted line is a little bit off, then the residuals are going to be different than the true but unknown. The residuals are going to be different from the true but unknown epsilon sub I. So this on the left, this epsilon sub I, is the error term that was added to the true but unknown mean here. And this, gosh darn it, small e sub I is going to be our estimate for what epsilon was based on the line we fit and how far off this value of y is from the actual y. And notice we're only going in the vertical direction because we're saying there's no uncertainty in the horizontal direction. We know x exactly. So the only randomness or deviation in the model is vertical. Okay, so from my sense, this screams out for an example. You can't really talk about it until you can see what's going on. So there's this table 11.1 in the textbook that talks about if you take solids out of sewage treatment, the amount of oxygen that the solids suck up gets reduced, presumably so more fish can live. And here's some data taken from that context. Right, I'm going to switch over to my spreadsheet and try and work our way through a couple of concepts here. Okay, is everybody seeing a spreadsheet? Anybody seeing a spread? Okay, so let me just delete this out. Okay, so I haven't fit any lines to this data, but I've taken the data that's here, I've put it into a spreadsheet, okay? And the blue line is the data just connected with the usual crap that Excel does. And then this orange line is going to be a fitted model. And right now I have that the intercept is equal to 0 and the slope is equal to 1. And that's a pretty boring model. Okay, so that says that right now all my fitted values that I have here are 0, because what's 3 times 0 plus 0? Well, it's 0. What's 7 times 0 plus 0? Well, it's 0. So my fitted values here are all 0, and that's a very interesting horizontal line. But what I've done is I've calculated the residuals from these models. So if y is equal to 5 and I said it was equal to 0, that's a squared error of 25. Okay. And let me take just a moment here to go on an excursion about why we use squared error. Okay. So let me see if I can start my visualizer here. I should have fired this up earlier, but it shouldn't take that long. Okay, so let's assume I'm on a rectilinear grid here. Let's put in an X, Y-axis, X-axis and a Y-axis. So we all see an X-axis and a Y-axis.
It's a little bit blurry, but yeah, we see it.
Let's see if I do something about this. Is that a little better?
Yeah, it is.
Okay. So now let's say we've got 2 points. Let's say we've got the point here and the point here. This is the point 1, 1, and this is the point 3, 2. Okay. So we've got 2 points on my graph. Boy, I got blurry again, didn't it? Let's see what we can do with this. I don't know why. Oh, there it comes in. Okay, so there's my points 1, 1 and 3, 2. What is the distance between those 2 points? Well, it turns out if we measure the distance this way, that we're going to take this distance. So we're going to take delta x and delta y. And we're going to say the distance is equal to the square root of delta x squared plus the change in y squared. Okay, so this is y2 minus y1 is my vertical change, and x2 minus x1 is my horizontal change. Does that ring any bells for people?
Yep.
Yeah. Well, this is called the L2 norm. This way of measuring distance is called the L2 norm. It's a real analysis topic. Reese, have you ever talked about norms in your math classes?
A bit, I think. It's familiar, though I could have just also looked into it on the side on my own.
Yeah, well, it's an important issue, so I'm going to tie it back into. But there's another way to measure distance. You could say the distance is equal to the absolute value of delta x plus the absolute value of delta y, which says that you take this distance and add that distance up, and that's what the distance is. And that's called the L1 norm. And if you ever try to give somebody directions in a city, you say you go over 2 blocks and then up 2 blocks, because you can't cut diagonally through the buildings, right? And this is called the L1 norm. Usually people don't get into very big discussions about which norm to use. But for linear algebra reasons and for optimization reasons, we're going to use the standard definition of distance, which means that if we want to find the distance between 2 points, we're going to square it and take the square root of that. Okay, makes sense?
Yes.
So yeah, well, maybe or maybe not, but that's all I'm going to say on it, because I would probably confuse you anyway. But the point is that I'm looking at that epsilon, or that, I'm sorry, that E sub I squared, because it's going to be related to what distance function I'm using and the mathematical properties of the L2 norm, or what I'm driving at. Way too much detail, but okay, we're off and running again. Okay, so back to my spreadsheet. So this is the difference between the fitted value and the observed value squared. And what I've done is I've summed all these, so I've taken all these ones and I've summed them up. So this is the sum of those E sub i's, and it's called the sum of my squared error, SSE, okay? So let's just try and fit some models to this by hand. Let's see, we go from 2020 to 4040. Let's guess that the slope is about 1 here. See what that does. Oh, that's actually a pretty good, much big improvement. And let's say the intercept is about 0.5 here. Yeah, it wasn't enough. Let's make it 1. Okay, so just by eyeballing this, I've gotten a pretty darn good fit, right? It looks like it's laying on top of most of the blue dots. Who agrees with me?
Yeah, looks like it.
Yeah, okay. But watch this sum of squared errors, okay? Because that's that is the measure of the total amount of how far off we are from that the fitted model is from the observed data. So when I had a 0.5 there, my sum of squared errors was 362. Okay, but when I moved to 0.1, it fit closer down here by the origin, but my actual sum of squared errors went up by about 4.5. And so it's a less well-fitting model in terms of minimizing the total overall area. Okay, so is everybody tracking with me that as I try different combinations of coefficients, I get a closer and closer linear fit? Yeah. So what this suggests is that there's an optimization problem buried in here someplace. That if I want to minimize the sum of squared errors by changing B1 and B2, that's an optimization problem, and that should ring some bells from calculus. So how do I find the values of beta 1 and beta naught that minimize this sum of squared error? You know, theoretically, not the actual calculations, but what's the underlying idea? Oh, come on, one of you guys has got to know the answer to this. I'll give you a hint. It involves derivatives. Finding optima by calculus.
My brain's saying something to do with second derivative, but that's about where I'm stuck, so.
Okay, well, so the idea is all extreme points are going to be either at the endpoints of observed values or someplace in the interior range of possible values of B1 and B naught. All the possible candidates are going to be where the partial derivatives are equal to 0. So if the derivative of the sum of squared error with respect to beta 1 is 0, and the derivative of the sum of the squared error with respect to beta naught are 0 simultaneously, that is either a saddle point, a maximum, or a minimum. And that's what we had from calculus. Now, skipping the pain of trying to actually take the, and you could write out what the sum of the squared error is in terms of beta naught and beta 1 and take those derivatives. But that's a half-hour pleasure in algebra and calculus that I'm going to skip. But I just wanted to remind you that that's how it's done, right? That you can, if you're trying to minimize or maximize a quantity, you take partial derivatives and set them simultaneously equal to 0. And the second derivative test that Reese has talked about is useful for classifying it as a minima or a maxima. Okay, so there we go. So that's the beautiful theoretical way to do it. What's another way to do it? Well, we've got this solver thing in Excel. So let's try to use the numerical search to find the values of B1 and B0 that make this quantity as small as possible. Okay, because that's really what our goal is. All right, so let's go to data. Oh, here we go, sorry. Where am I looking for? Data, solver. Okay, see, I'm clicking on the solver up here. And my goal is I want to set the cell J3, and I want it to be a minimum, and I want to change these two cells. Okay, and do I have any constraints? Nah, beta 1 and beta naught can both be negative or positive. So do we want to make the unconstrained variables non-negative? No. Okay, so we're not going to worry about the technical details here. We're just going to hit the solve button. Okay, so it goes off to Excel and thinks about it. Now it's doing a numerical search to trying to find the values of B1 and B naught that make this as small as possible. And apparently it's thinking about it for quite a bit. I did hit the solve, yeah, because it's grayed out, so it's still thinking about it. It shouldn't be this hard. Thinking about it, hoping I didn't break Excel. Okay, it converged to a solution. Oops, what happened? Gosh dang it, I hit the escape button too fast. All right, let's go to solve here again. And I'll give it the full couple of seconds here. Now, it shouldn't take this long to do it, but I believe I've got an awful lot of stuff running in the background. Yeah, I've only got 22 megabytes of background memory, so let me free some of that up. Yeah, freeing up some RAM. Okay, so it's still going and going and going. What do we expect this to be while we're waiting on it? What do we expect the minimum value to be? It's not going to, here we go. Yeah, it's not going to get a whole lot smaller than the 360 because there's still the random variation. But what this says is that the values of beta 1 and beta naught that give us the smallest sum of squared errors is this beta equal to about 0.9 and beta naught equal to 3.83. Okay, so that's one way to find the minima. And I'm going to have to, I apologize, run it again because I'm getting kludgy performance here. Options. Let's put a max 10 seconds on solving this and 150 iterations. We'll make it 15 seconds. I don't want to wait all day with this. Okay. So the most this should take now is 15 seconds to solve it. It's thinking about 1,000, 2,000. 3,000, 4,000, 5,000, and so forth. Well, this is bumming me out because I'm not getting the answer I'm looking for. Let's try it one last time. Take this off, take this off. Go, okay. So on a high functioning machine, and my machine this morning is not doing so great since I left it on all night, but here we go. Okay. I want to keep these values, so click OK. All right, so here I finally get my slope to be 0.903 and my intercept to be 3.83 roughly. And those are the numerically calculated values from a search algorithm to make that sum of the squared errors as small as possible. And what's interesting is that it's not trying to get the closest fit at the ends, but it's trying to get the closest fit for all of the points, and each point weighted the same. And that's why you're seeing it's got fairly good fit in the middle, and that's what's giving us the particular values that we have. All right, let me stop there. Do we understand the idea that we're trying to minimize the distance of the blue points from the orange points vertically, and that we're measuring that distance using the square of the value, and that we are trying to reduce that distance by changing the slope and the intercept of the line? Does that make sense for everybody? Yeah, okay. All right, let's go back and take a look at some slides here for a minute. And again, as you put different regression lines up there, and that's the fitted line, y hat with b naught and b1, we'll get different possibilities for the slope and the intercept because we don't know the underlying true model and there's random chance floating around. But the goal is to try and get the fitted line to be as close as possible to the true but unknown line. Okay, and again, I just want to hammer out this point. The variability, vertical variability in y is the same regardless of what value of x is. So for very small values of x, we've got the same variance as for very large values of x. We have the same variance. The distribution is constant around it. Okay. All right. So we showed one way to fit this line, and that was by minimizing the sum of the squared error. Let's talk a little bit about the calculus approach to doing this. Okay, so again, our goal is to find values of the estimated intercept and slope parameters, b naught and b1, that minimize the sum of the squared residuals. And that's what we showed on the spreadsheet. And again, a residual is defined as the observed value minus the fitted value. And that fitted value is beta naught plus b1 x1. And when we subtract off, we get that the residual is equal to the observed value minus the intercept minus the slope times the associated value of x. Okay, and we can square and sum up all these errors. The sum of squared errors is the sum of all these e sub I squareds. And what we do with that is we get this expression for the thing we're trying to minimize. Now, again, from calculus, we know if we take the partial derivative of the sum of squared errors with respect to the slope and the partial derivative with respect to the, with respect to the intercept here, and respect to the slope there and solve them simultaneously, that we will have all the candidates for the B naught and B1s that minimize the sum of squared errors. Okay, and that's gone over in the text in page 396 following. But I just want to show some of the notation that's used here to simplify this. So the sum of my observed values of X minus their average squared, the sum of that I'm going to call SXX. And the sum of my cross products, X minus its average times Y minus its average, I'm going to call SXY. Okay, and the sum of YY, I'm going to call this SYY, I'm going to call the sum of the Y's minus their average. Okay, so using this greatly simplifies the notation we're going on, and we can show that by taking derivatives that the values of B naught and B1 that minimize the sum of squared residuals are that sum of the X times Y, the cross products, divided by the sum of XX. That is the value of the slope that minimizes, and that the value of the intercept, if we take the average value of the Y's minus the slope times the average values of the X, that gives us our best estimate for the intercept. And that's what comes from solving Y average minus B1 X average, because Y average equals B1 times X average plus B naught. So if I know all of this stuff, which I do at this point, I can solve for this. Okay, so those are very easy formulas to remember, not that I'm going to require you to remember, and it makes the notation easy. Okay, so let's go back to our spreadsheet and play with this a bit. Okay, let me take these values that I got by search and copy those and just paste the values over here. Just for grins and giggles, and this was what we got by search. Okay, so let's go figure out what the sum of the X's, X's minus their average, the sum of the Y's minus their average, and these cross products are. That's a fairly easy deal. So this is going to be equal to parentheses, the observed value of X minus its average. I'm going to copy and paste this formula, so I'm going to put dollar signs there to give an absolute reference squared. Oops, I missed the 2 here. Squared. Okay, so I'm going to take all of these and copy this down. Boy, I'm getting really sluggish Excel performance today. Okay, and I'm going to take the sum of the XX, I'll put this over here, sum of the XX is going to be equal to the sum of all of these values. Okay, so far so good. Okay, let's do the same thing for the Y's. This is going to be equal to, open parentheses, the value of Y minus its average with an absolute reference with the dollar signs, close parentheses, squared. And I am going to copy this all the way down. And then I've already got the sum formula built in here, and that's going to come in as 3,700. And similarly for the XI's and the YI's, this is going to be equal to this value minus its average, absolute references, times the Y value minus its average, absolute references, close parentheses, and then we will write these all down. Okay, so this is my SXX, SXY, SYY. So what we said was that the slope should be equal to, just equal to the sum of these XYs divided by the sum of the XXs. What do we do here? Oops, delete. I put it in the wrong, yeah, here, I put it right here. Right, and what do I get? I get 0.90364 and change, which is pretty darn close to this 0.90363 that I got with the searching. Okay, that's the first comment. And this is supposed to be equal to the average values of the Y minus this H3 cell, which is my estimate for B1, times the average values of the X's. And what do I get there? 3.829, which is pretty close to the numerical answer I got with the search. Okay, so these are the estimates that we're going to use, and they're based on the solution of those calculus values. And my claim is that SXY divided by SXX is actually not that hard to compute. Okay, and somebody's trying to call me. Hopefully my wife will get that. Yeah, she did. Okay. So questions on the calculations for this? So the claim is that these two values for beta naught and beta 1, out of all the possible values of beta naught and beta 1, are the ones that that are closest to the observed data in the sense of squared error using this L2 norm. And it actually doesn't look that hard to calculate when you think about it. Okay, so this was that Excel exploration that we've just been doing. You know, we tried to hand jam it and got some different values and got the sum of the squared error down to about 360. Then we used the search term and used a numerical way that has no theoretical underpinnings. It's just doing a search to try and find the values that minimize it, and got it down to 323. And then we found the exact solution, gets us also down around 323, okay? But in practice, we don't do these calculations by figuring out the SX or the SY. You know, we just use software to do it. So we're running through it today so you understand a little bit about what's under the hood. Okay, so we've been looking at this data in table 1.1. We found the regression line using the solver. We found the regression line using formulas. Although I can't say this too strongly, hate the statistical functions in Excel, let's go through and use those to find the regression line, and then let's cut over to Minitab to wrap up these examples. Okay, so in my data tab, I have a data analysis button, which I'm going to hit. And under that, we have a choice for something called regression. Okay, and in this regression menu, I can input the Y range. And I can input the X range. And if I included the top of the column, I would click this labels that the first two entries are the names, but they're not, okay? And let's just put, although we don't need to put 95% confidence here, and let's have it put the output here for us on a different part of the spreadsheet. Let's put it over here, just off and to the right, okay? And I will take the fitted line plot as part of that. Okay, so let's see how fast that thinks. Spinning beach ball of death for our Mac users. Okay. So over here, we've gotten some regression output. Okay, and the important part for our point at this here are the coefficients. And it says that the intercept is 3.8296332. 3.8296332, that looks pretty familiar for the intercept. It says the slope is 903.64321. And that's, hey, no surprise, that's exactly what we got when we did the hard way. Okay, so those are pretty good. We'll talk Tuesday about what this R squared means for goodness of fit. But I just want to point something else about the regression error. Next to that coefficient is a standard error. Okay, who wants to tell me what they think that standard error is? Based on all the stuff we've done with confidence intervals and hypothesis testing using standard errors of a critical value plus or minus critical values times standard errors. Who wants to say what that is? It is what there's no surprises, but I'll just wait for somebody to articulate it. And I'm such an optimist because I should know after 14 weeks of this that it's like pulling teeth. But once again, I'm going to have a sip of coffee and hope that somebody jumps up and ventures a guess.
I'm going to go right ahead and say I have no idea.
Okay. That's an honest answer. Does anybody have even a faint clue?
Is it something to do with the average minus the observed minus the expected average over variance over square root of population? Or
yeah, so that's actually you're headed in the right direction, Sam. So what this is telling me how much uncertainty there is about this estimate for the coefficient. So I'm saying that this intercept is 3.8, but the amount of uncertainty of that is measured by the standard error of 1.76. And so if I assume this coefficient was normally distributed, which I'm going to do, and that I had a large sample, I could say I'm 95% sure that the true value of this coefficient is between 1.9, this value plus 1.96, and this value minus 1.96. Okay, and that would give me a confidence interval for what the true but unknown value of the intercept is. You should be saying, aha, I think I see where he's going with that. And it turns out I know the slope a little bit more precisely. This is only 0.05 times my critical value plus or minus, which means I might be between like 0.8 and 1.0 for my slope with 95% probability. Okay, so it's given me an indication of how tight my estimates are for the intercept and the slope. Okay, I'm going to jump ahead. So this t statistic is the value I get from the test of the hypothesis that the coefficient is really equal to 0, that the intercept here is really equal to 0. And there might, because there's a lot of uncertainty, excuse me, because there's a lot of uncertainty about what the value of the intercept is. Yeah, there's a 4% chance that I could get this value of the intercept just by chance given this data. So I'm not really sure that the intercept, I'm pretty sure, but I wouldn't bet my life the intercept is equal to 0. On the other hand, the test of the hypothesis that the slope is equal to 0, that's got a t statistic of 18 and a p-value of 5 times 10 to the minus 18. Now, I would bet my life that slope is not actually equal to 0, because the chance that I got these results is so far away from that as to be laughable. And actually, the lower, upper, and 95% confidence bounds for the estimate for the intercept and the estimate for the variable are calculated for you right there. Okay. And here is a useful plot of what the predictive values of Y were and the residuals. And we'll talk about that a little bit, hopefully on Tuesday when we talk about residuals. Okay, so here is a way to use Excel to calculate the coefficients, the standard errors, and to do a hypothesis test that they're really not equal to 0. Okay, I'll print it out for you. I kind of prefer, however, to do these types of problems in a piece of software that was designed to it. Minitab tries to be all things to all, Excel tries to be all things to all people, and it doesn't do necessarily such a great job. Okay, but let me come over here to Minitab. So I've got these same X and Y values plotted here, and I've gone to the statistics menu and popped open the regression menu and put fit regression model to pull down. And it's similar to Excel. It's going to ask me what's my response, and here it was Y, and what my predictor was, and here it was X, and X was continuous. And we're going to click OK. Okay, and then it gives us a little bit prettier output. So it tells us that this is our best fit regression equation, which not rounded to fewer significant digits. But not surprising, it's exactly the same thing we got with the search, and it's exactly the same thing we got with Excel. Gives us our terms here, the standard error, and again does the t statistic for the test that those terms could actually be 0 and reports the p-value. Excuse me. And this analysis of variance and fits and unusual observations we'll get to in a little bit. I want to redo this and have it add on to one plot though. I'm going to go to my graphs tab here on this, and I'm going to ask for all 4 of the plots to come out. Okay, so and I want to talk about this fitted value versus residuals. Okay, so the fitted values are given here, and then how much variability there is. And these residuals, according to our model, should look like a random draw from a normal distribution with mean 0 and with variance equal to 3.22 squared, or about 10. Okay, and in particular, I shouldn't see any patterns in the data. And so I don't really see any patterns in the data, but that's just a graphical diagnostic that what I've done is reasonable. And again, I get the normal probability plot for these residuals, and they look relatively normal, although there's some question what's going on up here in the tail here. And so we're going to talk again on Tuesday again about the graphical diagnostics for it. Okay. All right. So at this point, I think that's been a lot to think about. And we're going to stop right now. We'll answer some questions and talk about some stuff and get ready for the quiz. But in the meantime, next Tuesday, we're going to say, all right, so that B0 and B1 were estimators for the coefficients, so they have a distribution. So I should be able to do confidence intervals, which we just saw, hypothesis tests, which I just saw, and then using those estimators, I should be able to make prediction for a new value of X, what the fitted value would be. And then we're going to talk about these regression graphics that I hinted at here in a little bit more detail. But I think this has been a pretty big bite so far. So let me pause right there and ask if anybody has any questions or would like me to go over stuff again. stunned silence. That's how I would describe this. Okay, I see a question in the chat window. No question there. I see a note in the chat window that Moodle's back up. That's good to know. Would we like to try another example?
Sure.
One vote.
Or
All right, let's go back to our Excel spreadsheet. Let's start a new tab. Make a little bit bigger. Oops, too much. And let's call this come on. All right, let's just call this example. Okay, so let's make up an X. Let's make it be from 1 to 10. Okay. Let's have a true beta naught and a true beta 1. Oops. Okay, and let me just come in here with home. Got a symbol, beta naught, and make this again the font be the symbol font. Say these are the true values. Okay, so somebody give me an intercept. Just make something up. Chat window or talking, I don't really care. 5, okay. And somebody give me a made up slope. It can be positive, negative, or even 0. 2, okay. All right, so the other thing we need is we need a sigma squared. I have to put this in quotation marks so it doesn't think it is actually referring to the cell S2. Okay, and how tight do we want this estimate to be? What do we want the variance to be? One, 2, 5, a half,
0.5.
0.5. All right, dandy. Okay. All right. So let me make up some. Let's figure out what our expected value of y given x is. Okay, so we know that what this is exactly. This is going to be equal to 5 with the absolute reference plus, come on back over here, baby. 5 plus the slope times whatever the value of x is. Okay, so let's see. 5 plus 2 times 1 is 7. That looks about right. And let's copy it all down. Okay, so we have our nice linear model. And then our variability, our epsilon, is going to be equal to a random draw so I want a random variable that has mean 0 and variance 0.5. So let's see, that makes sigma. Let's just find out what the God dang it, I'm in the wrong cell. Come on over here. So sigma is going to be, the standard deviation is going to be the square root of this 0.5, which is, I think, 0.707. Yeah, okay. So, so this is going to be I need a random variable that has a normal distribution that has that variance. So I'm going to go equals norm dot inverse. Okay. And I'm going to use a random number generator for the probability. And the mean is going to be equal to, let's just say 0 here. And the standard deviation is going to be this quantity, Command Control T. Okay. So I've, copy this down. Okay. So I know the true model here. I know the distribution of the error. And now what I'm going to do is come up with my observed Y. Okay. Which is going to be equal to, the expected value plus epsilon, the true error term. I just copy this all down. Okay, and now to stop it from constantly jumping up and down, I'm going to take these error terms, which change every time I hit the key. I'm going to copy them, and I'm just going to paste the values in to lock things from bouncing around again. Right, delete. Okay, so these are the Y's that my theoretically unknown experiment would have generated for me. Okay, everybody's with me so far? Actually, let me take this epsilon and move it over to the right here a little bit. And put this here. Okay, cool. Let's use Excel to fit this model for us. Okay, and we'll put input range for X will be here, and input range for Y will be here. And this time I'm going to include the column labels. Oops, don't want that column. I want this column. I want the observed values of Y. Okay, so copy those down. Messiah, I do have the labels. And I'm going to put the output range to be right here because we don't need that much, and click OK. Okay, so it goes through and it gives us the values for the coefficient, for the intercept, and for the observed slope right down here. So let's put those here. So the intercept value we had was equal to this value. And then the slope value we got was equal to this value. So what happened here? When I did my observed value of Y, I put I have my error term plus my value here, but I've left off the formula for my intercept, which is why everything is off 5. Okay. That's why I've made up bad fake data. That looks better. Let me just quickly run through this data analysis menu again. Okay, so it runs through it again. And now I've got an estimated slope that's much closer to 5. And a slope value listed there. Okay.
Did you perhaps switch the X and Y variables when you're
I'm
putting it
wondering
in?
if I'm thinking that's exactly what I did when I put it in. Yeah, good catch. Let's try this one more time. Because yeah, it's not looking right. Okay, so what is my Y range is column F. That's my observed value of Y. And my observed value of X is this. And I don't have the labels. Last time should be a charm. Okay. All right, well, this is what happens when you make examples up on the fly. That's now way too off.
You put the slope as the intercept. Where you have
Thank you.
D1.
Okay, so
No, on the observed Y values. Never mind, I'm going crazy. I forgot that
okay,
beta
so
0
what?
is the intercept.
So we're saying that this is going to be equal to the true value plus the error term. All right, yeah. Now I've double added the intercept in because it's already in the built-in value for expected value. Okay. All right, last time. There we go. All right, last time was a charm, and I'm just about out of time too, but okay. So now I've got data where the 7.2 is close to 7, and the 9 is close to the right value. And I've got my estimates coming in, yeah, close to 5, close to 2. Okay, so the problem was creating the data. Now that I've created data from my model, the point of this example is I know the true values, and I did a random draw, and I found out how close I got just by chance. And so I can go down and look at these confidence intervals I have here. It says that the intercept should be between 4 and 6.4, and 5 is, and that the slope should be 1.76 to 2.17 or 2.15, and it is. So I've showed that my model confidence intervals I construct here capture it. But this goes back to the comment discussion I had with Rocky a while ago, which is never make examples up ahead of time on the fly because something always goes wrong. Okay, good. Let me stop. I should have stopped before. Okay, so we'll pick up and talk about this in a bit more. I am going to post the quiz problem. The quiz is similar to one of the homework examples, but read it carefully because you have to, the whole point of the quiz is getting the null hypothesis right, and everything else follows from it. But you have to think about it a bit carefully. So I'm going to post that quiz out. I'd like it back by, I think I said noon this time, because people are having trouble getting stuff mailed back and forth. And I'll take any questions people have at this point. All right, let me spend a moment summarizing. We opened the class talking about lines, which is a model where you have one or more predictors, each with an associated slope and a common intercept. And we talked about fitting lines. We talked about why we use squared distance as our estimate of distance as opposed to the absolute value. We set up a spreadsheet with some data in the book, and we found out what the average of the x's was, the average of the y's were. When we calculated how far y was from its average, squared it, summed that to get SYY, similar with SSX and SXY. And then we went, accepted on faith the formulas are in the book from calculus, that the slope is the SXY over SXX. That's the value of the slope that minimizes it. And then using the y average, the x average, and that slope, we can solve for what the best fitting intercept is. We did that, and we went through an example or two, and we closed with my disastrous attempt to make some data up and show that it still works for made up data where we actually know the model. Okay, so that's my summary. Last call for questions. Okay, then I will log off of this, stop the recording, and post the quiz for you. And we will see you on Tuesday when we start the last week of class. I can't believe it.